All right, everyone, this is Dr. Zach. So today we're going to use our implicit differentiation to begin working on related rates problems. Related rates problems are going to be one of the hot topics in our AP Calculus course. So let's get started. For today's lesson preview, I wanted to make certain that you are really adept at using your chain rule as well as the product rule. So as I'm looking at question A, you should have 6. Keep the inside your x squared plus y squared raised to the first power, but then we need the derivative of the inside, which would be 2x plus 2y dy dx, since we're looking for the derivative with respect to x, and that's going to be equal to 100. Using the product rule, we will have first times the derivative of the second plus the second times the derivative of the first, which happens to be good old 1. Now, from here, you're going to substitute in your 3 and your 1 as your x and y's, and my suggestion is that you do it right now before you get too far along in the problem, and that should make your life just a little bit easier to solve for your dy dx. Do the substitution first, and then dy dx will be just a little bit easier to find. For your second question, I wanted you to practice finding the derivative with respect to a different variable. So if you're looking for the derivative with respect to t, you get your dA dt equals 2s, and then we're going to use a chain rule and write ds dt. So what could dA dt represent? Perhaps you know that it's the area of a square, so if time is represented by t, this could be how fast the area of a square is changing. For today's first example, what we're looking for is the second derivative, and we want that second derivative with respect to x. Of course, we're going to find the first derivative. So we have our 2x plus 2y dy dx is equal to 0. Remember that 0, very important. When we solve for dy dx, we end up with negative x over y. So the first derivative was not very challenging. And now let's find the second derivative with respect to x. So we get our d squared y dx squared. It's written this way so that it doesn't look like we're taking a derivative and squaring it. Instead, we're going to use our quotient rule. So we'll have the bottom times the derivative of the top minus the top times the derivative of the bottom, which is dy dx over the bottom squared. So there's your y squared. Now what you should notice is our derivative has a dy dx in it. We're going to substitute. We have negative y plus x times negative x over y divided by our y squared. Now, in order to simplify this function, we want to multiply by y over y, and that should make this a little bit easier to deal with. And once we simplify again, we have negative y squared, negative x squared, divided by y to the third power. Now, when you look at negative y squared, negative x squared, what I'm hoping that you see is that this is actually negative 25 over y to the third. Now, if you're thinking about that 25, go back to the beginning problem where we're told that x squared plus y squared is equal to 25. Replace, and we have our second derivative. For example 2, we're looking for the derivative of r with respect to t. So you might recognize this as the surface area equation for a cylinder. If not, write it down because you're going to need to know it. We're finding the derivative with respect to t. D, we'll call this SADT, equals. Now, hopefully you've recognized you have just one product rule in here. 2 pi r is a variable expression. We'll call that the first. And what we'll have is first times the derivative of the second, which is your dH dt, plus the second, which is h, times the derivative of the first, which is 2 pi dr dt, because the derivative of r with respect to t is going to stay. The second part is not a product rule, but we do get plus 4 pi r to the first power times dr dt. All right, so what you'll notice here is that we have dr dt in two parts of the expression. And oh my goodness, let's count the variables. For this problem, we have 1, 2, 3, 4, 5 different variables. Originally, we had 1, 2, 3 variables, and now we have 4. Anyway, we're going to take this problem. We're solving for dr dt, so I'm going to rewrite it as derivative of the surface area with respect to time, minus 2 pi r dh dt is going to be equal to, let's do some factoring. Here's your dr dt. We're left with 2 pi h plus 4 pi r. And now we're ready to divide your dr dt. And we have the derivative with surface area with respect to t minus 2 pi r dh dt divided by our 2 pi h plus 4 pi r. So we found the dr dt, which could be the derivative of the radius with respect to time. So for example 3, we have the formula for the area of a triangle. Now this triangle in particular has 2 sides and the included angle. So if you were to find the area of a triangle with 2 sides and included angle, you could use this formula. Now, for this particular problem, we want to know d theta dt. So how fast theta is changing with respect to time. It looks a little complex. Do you notice in here we have a triple multiplication occurring? So let's find a derivative with respect to t. dA dt is going to be equal to, I'm going to call 1/2 x the first. So we have the first times the derivative of the second, which of course is a product rule. So we will have first derivative of the second. So there's your cosine theta d theta dt plus the second, which is your sine theta, times the derivative of the first, which is dy dt. All right, so let's recap. This was our first derivative of the second. Plus, we'll have the second term, which was y sine theta, times the derivative of the first, which is 1/2 dx dt. Now, in particular, we were told to find d theta dt. So we want to move every expression that does not have d theta dt. So we have dA dt minus y sine theta, 1/2 dx dt, minus 1/2 x times the sine of theta, dy dt, is going to be equal to your 1/2 xy cosine theta, d theta dt. And then a little bit of division, you will have what you're looking for. So for this problem, we had a triple product rule. But as you can see, as long as you declare what's first and what's second, you can find your derivative with little trouble at all. And we now know d theta dt. So let's take a look at example number 4. The distance equation was used to write this equation. Distance equals the quantity x minus 2 squared plus x cubed. We're going to determine how fast x is changing. So that means find dx dt at x equals 2, given that dd dt equals 10 when x equals 2. So we were given information this time. So looking at my function, I have d. I also have the square root. That is annoying, so I'm going to square both sides, make this a little bit easier on myself. So I'm going to look at d squared equals the quantity x minus 2 squared plus x cubed. Now let's find the derivative using implicit differentiation. We get 2d dd dt is equal to 2 times the quantity x minus 2 times the derivative of x with respect to t. The derivative of 2, of course, is 0, plus 3x squared dx dt. All right, now let's recap. We want to find dx dt. when x is 2. But we also know that dd dt is 10. Okay, so let's fill some information in. We have 2. I don't know d. We'll come back to that. dd dt is 10 equals 2. X is 2. Oh, so this is 2 minus 2. That's convenient. Plus 12 dx dt. All right, so the only thing that's missing now is d. But if we go back to our original problem, we can see d equals the square root of 2 minus 2 is 0, plus 2 cubed, which is going to be the square root of 8. All right, so now we know d is the square root of 8. Given that, we can find dx dt. So we will have 40 root 2 divided by 12 equals dx dt. And then, of course, we will reduce. Let's look at the lesson practice together. Our first question is asking, how fast does the area of the paint spill spread? So we're looking for dA dt. And then it continues, if the radius is changing, so that's some given value, dr dt, and that dr dt is given to you as 5 meters per second when the radius is 2 meters. So we're looking for dA dt. We use that line for when r equals 2. We have our given and we have the question. Find that derivative and see if you can answer the question. For question 2, how fast is the height changing? Well, that's telling you find dH dt. When the volume is changing at a rate of negative 10 meters cubed per hour, and the radius is 2 meters when the height is 5 meters. So the question is asking for dH dt when r equals 2 and h equals 5. But you're also given that dV dt is equal to negative 10, now look at your units, meters cubed per hour. So this would be a volume, there's your cubed, per hour, because that's your time. Give this question set a try and check your answers when you're done. This question, find all points for which the graph of the equation has vertical and horizontal tangent lines. So if you have a horizontal tangent line, you know that your dy dx is going to be equal to 0. When you think about your vertical tangent lines, that's where dy dx does not exist. But what if we were to think of it as where dx dy is equal to 0? So that's something to contemplate as you complete this problem set. Normal lines are perpendicular to your tangent lines. So if you're perpendicular, keep in mind that the slope of the tangent line is going to be the opposite reciprocal. So you have your opposite reciprocals for normal lines and perpendicular lines. So today's lesson follow-up, you have a series of questions. Give these a try and let me know if you need any help. You have a fabulous day.